Hello everyone, this is Dr. Chen. We're going to study rotational motion in this lecture video. Rotational motion is highly related to gravitation. So we study the definition of rotational motion and then we'll move on to apply it to planetary motion. So we have learning linear motion, and we have been treating objects as particles. Now for rotational motion, now we need to treat particle as a rigid object. The definition of rigid object: the distance between any 2 points on the rigid object doesn't change during the motion. Now when this figure is skating, let's pick 3 points A, B, C. And when the figure skater is spinning, distance between A and B, B and C doesn't change. And we need to generalize this to any point. At any point, the distance between any 2 points on this figure skater doesn't change. So it's a rigid object in this rotational motion. So in a simplest kind of rotation, points, a rigid body moves around an axis of rotation. So in this example, we have this as our axis of rotation, and then any point is doing a circular motion around this axis. The distance between any points to the axis doesn't change. Any points is doing a rotational motion around this axis. So this is rotational motion and a rigid object. And from now on, we are not going to use angle for degree for angles. So the unit we're going to use for angles is radians. And how it was defined? It coming from the definition of if we have a circle and this arc divided by radius give us the angle of this, the radians of this angle. So if we can recall how do we calculate circumference? Circumference equals 2 times pi times r. So by definition, this entire circle, this angle is 2 pi radians. So which means from x to y, this 90-degree angle is 1/2 pi. And for 45 degree would be 1/4 of pi, pi of 4 radians. So this is how radians was defined. So we can do unit conversion now. 45 degree is pi over 4 radians. So what is 1 radii? What is 1 radians? What is 1 radians? So because we know 4/5 radian equals 45 degree. So we need to multiply by a 1, right? So we can change the left-hand side to 1 radian. So we need to do a 4/pi multiply both sides, and pi is a number. So left-hand side will give us 1 radian, and right-hand side will give us a degree, 4/pi, which is roughly 4 divided by 3.14 times 45 degree. So this is what 1 radian is. So 1 radian is 4/pi times 45 degree. You plug in 3.14 for pi, we roughly get 57.3 degrees. So 1 radian is roughly 53.3. Sorry, 1 radian is roughly 57.3 degrees. And for the angles, we need to define where is angle 0. So usually we would choose the positive x to be 0 radian. And we would define counterclockwise rotation as positive. So this is a positive angle, counterclockwise. So again, positive x direction would be 0. And then counterclockwise is positive. Clockwise is negative. And this is positive. Clockwise and counterclockwise is related to the clock. If we look at the motion of the hands on the clock, the hands are moving this way, so we call it clockwise. So counterclockwise is in the opposite direction of how the hands moving. This is counterclockwise. Now we're ready to define angular displacement. So this is angular position. Angular position. We have a point that doing rotational motion. This is initial angular position, theta I. And then it rotates to a position B. We call this angle is final angle angular position. So the angular displacement is theta F subtract theta I. And again, by convention, this is a convention. Angular displacement is positive if you rotate counterclockwise, and it's negative if you rotate clockwise. And we always use the SI unit for angle is radian. A degree is not SI unit. So for example, if the initial angular position is 4 radian and the final angular position is 7 radians, while this A and B does not necessarily corresponding to those two angles. Initial angle is 4 radian, final angle is 7 radians, and the angular displacement is 3 radian. Now, after we defined angular displacement, we're ready to define angular velocity. So if you can recall, average velocity was defined as displacement over time. So you can expect we're going to define angular velocity in a very, very similar manner. So angular velocity, the magnitude is defined as the magnitude of angular displacement, which is final angular position subtract initial angular position divided by time it takes for such displacement. This is angular velocity. So if we take this delta t to be very, very small, we get instantaneous angular velocity. Example. So we have a gymnast on high bar swing through 2 revolutions in a time of 1.9 seconds. What's the average angular velocity? So we know the time. We want to find angular velocity. So we need to find angular displacement divided by the time. Already know the time, we just need to find angular displacement. And it tells us 2 revolutions. Means 2 complete circles. So if the gymnast does 2 revolutions, what is the angular displacement? 2 times 2 pi, right? Because 1 revolution is 2 pi in radians. The rotation is in clockwise direction. So the angular displacement is 2 times 2 pi, negative 4 pi. The number should be negative 12.6 reading. That's the angular displacement. So the angular velocity is angular displacement divided by the time. Yeah, so we find the answer. And Let's first recall what's the definition of acceleration. Acceleration is change of velocity divided by time. So that's how we define angular acceleration. Because angular velocity can change, so the change of angular velocity divided by the time it takes for such change of angular velocity divided by time for such change give us angular acceleration. Angular acceleration is the first letter of Greek letter alpha. So if you noticed, we're using almost all Greek letters for angular motion now. Acceleration we use alpha, and we use angular velocity we use omega for angular velocity. So definition of angular acceleration, change of angular velocity divided by time. So if we know final angular velocity, initial angular velocity, we know the time, we can calculate angular acceleration. Now in this example, initial angular velocity 15 reading per second, final angular velocity 9 reading per second, time is 3 seconds. What's the angular acceleration? Change of angular velocity, final angular velocity, 9 reading per second, subtract initial angular velocity, which is 15 readings per second, divided by the time, 3 seconds, give us -2 readings per second squared. And the unit for angular acceleration is reading per second squared. Example. So we have an engine. The fan blade rotating with angular speed. This initial angular speed, -110 reading per second. And then it started to accelerate to a final angular velocity of -330 reading per second. The time is 14 seconds. What's the angular acceleration? So we just need to use the definition of angular acceleration, right? Change of angular velocity divided by time. And average angular acceleration equals final angular velocity subtract initial angular velocity divided by time. And it gives us -16 readings per second squared. Unit for angular acceleration is reading per second squared. The unit reading doesn't have, actually the dimension is 1. The dimension of angle is 1. So actually the dimension of angular acceleration is 1 over t squared. And the dimension of angular velocity is 1 over t. If we take the time interval to be very small, then we get instantaneous angular acceleration. Let's first recall that in linear motion, if we have a constant acceleration a, we have some kinematic equations, and we use those 3 equations very often if we have constant acceleration. So similarly, in rotational motion, if we have a constant angular acceleration, by definition of angular acceleration is final velocity subtract the initial velocity divided by time. So if we multiply delta t on both sides, angular acceleration times t gives us change of angular velocity, right? So similarly, we are going to have this equation. So in linear motion, constant acceleration, we have final velocity equals initial velocity plus acceleration times t. in constant angular acceleration motion, final angular velocity equals initial angular velocity plus angular acceleration times t. There is a one-to-one correspondence. And then we can derive for constant acceleration motion, displacement equals initial velocity times t plus 1/2 at squared. In angular constant angular velocity motion, constant angular acceleration motion. If we have constant angular acceleration motion, then we have displacement equals initial angular velocity times t plus 1/2 angular acceleration t squared. There is a one-to-one correspondence. So basically, we just need to do a mapping from final velocity to final angular velocity, initial velocity to initial angular velocity, acceleration to angular acceleration t, and then displacement mapping to angular displacement. We have exactly same mathematical form of three equations. Now the last equation, the third equation, v squared equals final velocity squared equals initial velocity squared plus 2 times acceleration times displacement in angular motion with constant angular acceleration. We have final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration. That's 4. So the problem solving strategy is almost exactly the same as we did in chapter 2. So first we make a drawing, decide which rotation direction we want to be called positive and negative. Now we should follow the convention. We always choose counterclockwise to be positive. Write down the values that are given for those 5 kinematic variables and then figure out which variable is asking. And we should know at least 3 variables, then we can choose operator the equation to solve the unknown. Yeah, so you should be expert in this. Nothing is changed except there is a mapping between linear motion and angular motion. Blending with the blender example. So now we know. So this is angular velocity. Let's read the problem. What kind of velocity is that? Is initial or final? When the blend button is pushed, blade accelerates to reach a great angular velocity after the blade have rotated through angular displacement of 44. So this is angular displacement. So we know delta theta. The angular acceleration is, we know the angular acceleration. Find the final angular velocity. So after reading the question, we kind of figure out this. What's given here is initial velocity, initial angular velocity, angular acceleration, angular displacement. It asks us what is final angular velocity. So we know initial angular velocity. We know displacement. We know angular acceleration. So we need to figure out which equation contains these 4 variables. We can flash back to what we have. We want to find this one. We want to find this one. We know initial angular velocity. We know angular acceleration. We know angular displacement. So I would use this equation to solve this problem. Right? So we see we have angular displacement, angular acceleration, initial angular velocity, and we want to find the final velocity. So we use this equation to solve it. We just need to square root the right hands, plugging all the numbers. We find the final angular velocity action is 542 radii per second.